Hello. So, um, I had this idea last night to make a prisoner's dilemma sort of thing. Um, to make a kind of a simulation of like the iterated prisoner's dilemma. And so basically, if you are not familiar with what the prisoner's dilemma is, basically it's the idea that you you have a friend and you can either say I love you or I hate you to this friend. And then your friend can do the same thing. You can say I love you or you can say I hate you. Now, if you both say I love you to each other, then you get 3 and he gets 3. Um, I'll wait to write that in so I can write it in all at once. If you say I hate you to him, you get 5, but he gets 0. If he says I hate you and you say I love you, then you get 0, but he gets 5. And then if you both say I hate you to each other, then you both get 1. So the idea with the prisoner's dilemma is that if you both say I hate you, you get less together than if you both say I love you to each other. This is 2. This, the group gets 5. This, the group gets 5. And this, the group gets 6. But it makes much more sense for you to say I hate you from a selfish perspective. Because no matter what, if you say I hate you, no matter what situation you're in, you're going to get more cookies. Problem is, that hurts the group. So this is called the prisoner's dilemma. Basically, it's usually introduced as like, you got caught for some crime, and you want to, and you and your friend get caught for some crime, and you have to like confess. But you can only confess to the other person's crime. So if you confess to the other person's crime, you get less years. Pretend that this is like the other way around, where it's like you want more years in prison or whatever with these numbers, or like, these numbers are like kind of switched. So this is 5, this is 3, this is 1, this is 0, or something. So, you get away for free, but they get 5 years in prison if you confess to them, but they don't confess to you. But if you both stay silent, you both get more years in prison individually. But no matter what, if you defect to the other side, you can always get less years in prison. Let's just go with the cookie analogy for now, because that just makes more sense with the specific scores that we have listed out here. So no matter what, saying I hate you gets you more cookies. But if you both say I hate you, that's just worse for the group. You're selfish. You're taking more from the group. So that's the prisoner's dilemma. Now, the iterated prisoner's dilemma is doing this over and over again. So in general, cooperating, there's more of an obviously there's more of an incentive to no matter what defect, but that's going to affect your relationship in the future. So the iterated prisoner's dilemma is doing it over and over again. And so you'll tend to see more people wanting to cooperate more often because it's just better for them. It's going to be better for them in the long run because they're going to get more points in the long run than if they defect. It becomes really interesting because, depending on the other person's strategy, you can take advantage of it. So there's a few different strategies to the iterated prisoner's dilemma, and we'll just go over some like kind of simple ones. So obviously there's like always cooperate and always defect, which always defecting, you know, eventually over time, a lot of the times, competing with other people, it just ends up worse off because then they always defect in order to, you know, they'll figure out, oh, there's no way I can negotiate with this person to get a better score, so I'm just always going to defect as well. So this usually doesn't end up very well. Always cooperating, however, can be taken advantage of. So, always cooperating is going to mean that you basically, I'm going to make it like this because this looks nice. It's nice like this. Okay, maybe not. You get taken advantage of more often than not because they learn that they can just always defect. The other player learns that they can always defect and they can always get a better score. So, how about this one strategy called tit for tat? It's pretty simple. It sees what the other person did and it retaliates them. It retaliates. So it doesn't, it's very similar to the always cooperating, and it always starts out cooperating, but if somebody tries to take advantage of it, it will retaliate, and it will say, it will defect next time. So, you know, maybe you have cooperation in the first round, cooperation in the second round, cooperation in the third round. Then if somebody tries to defect, they don't know that they've defected this round, but in the next round, they'll also defect. They're retaliating, so they can't really be taken advantage of. It's like, yeah, you give me this, I'll give you that. And so it is actually fairly successful. There are some more strategies. Like, for example, there's Joss, which basically attempts to it will kind of no wait, no, that's not Joss, that's Tester. I completely forget what Joss is, but there's a strategy like Tester, which will sometimes randomly test tit for tat. Tit for tat is a very good strategy. Tester will sometimes randomly tests the other player. So, if it finds that it can work, it will then try to take advantage of it. No, wait, no. Is that Joss? No. No, I think that's Joss. Yeah, because what Joss does is JOS kind of tests for the always cooperating strategy. So if their strategy is always cooperating, JOS will try to uncooperate, try to defect, uncooperate, will try to defect. And if they don't retaliate with anything, then they'll just keep defecting because they know that they can take advantage of it. So these guys end up racking up a lot of points. And then always cooperating gets taken advantage of. So there's a whole bunch of different strategies. But I think I have an idea for how I want to make a simulation of this. Basically, I want to be kind of like a genetic algorithm, and I want there to be like an environment that they grow up in, that they survive in, and I want to watch how they evolve, what strategies come to the forefront, and what sticks around, and I kind of want to make like a simulator for it. So here's how I want the brains of the machine to work, of the players to work. And this can cover a lot of the different strategies that are around. So the machine has a bunch of different states. A, say B, say C, and I think I want there to be like 10 states. So each state, it's going to start off on the A state, and each state will either be a cooperating state or a defecting state. We'll just color this in. Oops. Yeah, no, never mind. We'll just go brush. Each state may be a cooperating state or a defecting state. And so, the machine moves from state to state, and depending on what state it's on when the round starts, determines whether it cooperates or defects. So it's a lot like a Turing machine. So then, depending on the state it's on, it sees what the previous person did, and it responds. So, depending on if it cooperates, it'll go to one state, or it'll go to a different state. And then once it's on a different state, it can, depending on if it cooperates, if it defects or cooperates, it'll go to a different state. So like maybe B goes to C when it corrects, when it cooperates, but when it defects, it goes back onto itself or something. Who knows? And so basically, a mutation, it'll start off, all of the machines, or all of the players, will start off randomly with each state assigned to a different state. Like, let's say, I think J is the 10th letter of the alphabet, okay. Like, maybe if it cooperates, it goes to I, and then if it defects, it goes to D. Then on B, if it cooperates, it will go to C. If it defects, it will go to, like, A or something like that, And these will all be completely randomly generated. ... And a state can either be a cooperating state a defecting state, or it can be a random state. And this random state has a certain probability to it. And those numbers start off like completely randomly. So like let's say it's 0.12, like 4 ... I don't know. And that is the probability that it defects versus cooperates or something. And mutations can change these numbers over time, of course. So, basically, a mutation can change any one of these letters, or it can change whether the state cooperates or defects, or it can change the probability. Of something, of a random state. And I think just to make it simpler, I'm probably gonna have, let me switch to this, B. Just to make it simpler, I'm probably going to have it so that, each state just has a random number associated with it. And then if it is random, then it will choose from the random probability. Just to make the data a little bit easier to organize. So, with this, you can kind of have a lot of, you can kind of make a lot of the strategies that I was talking about here. So you can have an always cooperate by just having A, and then if the other person cooperates, it goes to A. Otherwise, it goes to A again. So it always just loops back on itself no matter what. And that always cooperates. You can have the same thing with always defecting, where it's just literally the same thing. And you can have more complicated versions of these that do exactly the same behavior. So like, for example, you could have something silly like, you could have A, but if they cooperate, it goes to A. If they defect, it goes to B. And then B is always cooperating, and if they cooperate, then they go to, I don't know, B, and then otherwise they'll go to, or sorry, if they cooperate, then they'll go to A, otherwise they go to B. And that just kind of always leaves you in a loop of constantly going back and forth between A and B, and they're going to be in, and they're always cooperating. So there's a few different ways to develop the strategy with this method. And each brain is going to be very different from each other. Like, it might be something like I and D, or, F and J or something. Who knows? But they'll always start off on A. They'll always start off the match, or the generation on A. Or, well, yeah, the match. I don't know, I'll kind of get into that later. But it's easy to develop tit for tat if you just change this right here to a B. Now, if they cooperate, no matter what, it goes to A. They defect, goes to B. And then they'll defect next round. Same thing, same deal. There is a different strategy called, there's another strategy called forgiving tit for tat, which kind of basically has two, you have to defect twice in order for them to defect. So you can start off with something like, you can do that pretty easily by saying, you know, you have A is cooperating. If they cooperate, then go to A. Otherwise, go to B. B is also cooperating, but if they defect, and if they decide to cooperate again, they're always going to be on B if they didn't cooperate. If they cooperate again, you go to A. Otherwise, you go to C. You know, so if they've not cooperated twice, and they'll just go to C. A, otherwise go to C. And you can change that up by saying, okay, you can make a super forgiving tit for tat, I guess. I just made that up right now, where it goes back to B. You know, so if it defects, it'll be like, okay, I'm sorry. And then if you keep defecting, then it will go back. And so it'll go back and forth between not affecting and defecting. But no, traditional forgiving tit for tat would just go back to C. It would just keep defecting until you stop defecting. So, and of course, through the genetic algorithm, through mutations, eventually these things will kind of develop, and we'll see them. What else? Oh, you could have something like a tester or a JOS by having, you know, A is random. If they cooperate, go back to A. Oh, I just realized something. There's no way for the machine to tell if it defected in that round or something. That's interesting. Let me think about that. How about in the case of a random? That'd be interesting if it didn't know what it put out. I kind of want it to know, though. So, what if instead we did randomness a little bit differently? So as in, like, randomly, it might, no. This doesn't work like Krita. How about randomly? Like maybe there's a random flag that sometimes comes up. So, you know, each brain has like it's like an X, like a check, or each state. And the randomness flag is kind of rare, but when the randomness flag is activated, there's also going to be another random thing. There's also going to be another random state. Like, let's say this is like F. This was like H or something, you know. When the randomness flag is activated, and then each one, of course, has a random number. So this is like 0.621 or something. Did I really just do that? I was just randomly coming up with numbers, and that happened to come up. Wow, that's amazing. This could be like, I don't know, 0.058 or whatever. It will, you know, it might have the random flag set, and if it has the random flag set, regardless of before it does anything, it will randomly jump to this state. If the random flag is set, it'll just randomly decide to jump to the H state. And then it will do whatever it's on the H state. And then it will react accordingly. Okay, that works. It's a little bit more complicated than I would like. There's a lot more information in each state than, you know, I would like, but I think that'll work, you know. So we could have like a tester with that idea. Okay, let me actually see if I have any. Let me see if I have any messages. I don't think I do. Okay, so I think we have this idea. I'll try to put this off. I kind of know what it is in my head, so I'll just kind of minimize it, I guess. And yeah, let's start designing it. So, I think what I'm going to do is I'm also going to start the simulation, at least, you know, just to kind of see it. I'm going to start the simulation off with some completely randomly generated creatures. But then I also want to start it off with some, like, completely normal creatures, like the tit-for-tat creature, you know, some ones that we already know about. Or, like, you know, start off with some always defecting. So, I am going to make a constant called brains. And I'll make that be an object. I'm going to use a lot of objects today, I feel. I'm not entirely familiar with how to use objects, so let me look at objects, JavaScript. Let me see this. I think I kind of know how they work. Yeah, I know how to deal with these. Just need a refresher because I haven't used them in so long. Okay, yeah. So, do this and do with colons. So let's say, yeah, let's make it kind of like this. And I want an example brain. let's sort of design this up here. Oh, we can. So, I think what I want... Oh, I should probably have left this up a little bit to just kind of go over my... let me put my drawing tablet back in place so I can draw this out. There we go. So, I want to have a brain, and that brain will have a bunch of states. Or I want to have an individual, and then that individual will have an ID. Maybe we'll also have a life, so how long it's been alive. Maybe we'll have a hash of the brain hash. Might also have a color that might be based on the brain hash. These two related. And then we will have states. I kind of want to call this the brain. But I also want to call it states. So yeah, I guess I can call the default brains sort of brains. And I can say generate brain, you know. So this will be an array. And then these will have inside of them they'll have an action, I'll redraw this a little bit to represent what I want to show. They'll have actions. They'll have C jump, defect jump, and then R jump, R value, that's the random value, and then they'll have R flag. And I think I want a state to be an object, and then I want there to be an array of states. Alright, so let's say something like, let's go here, say constant brains equals and I'll put this away now. Bead conchoperator. I don't know what the fuck that means. It's one that was randomly generated. Iterated prisoner's dilemma. Okay. So, start off with this constant called brains. So, we'll say tit for tat. will be this brain. And we'll just list an array of the states. A state is an object. So we'll have 10 objects. We're only really going to be using 2 states, so we'll leave all the rest as like kind of not blank, because that just, you know, you don't really want to do that, but as kind of dummy filler material. Kind of just the same thing. So we have, let me move all this stuff over. Action. And we'll say, we'll add in a convention here that cooperate is true and defect is false. We'll just keep that in mind. So we'll say action. We're going to cooperate in state A. Actually, we're not going to do, we're going to have numbers here because we have an array, and that makes it easier to work with, you know. So you can just call like array 0. You can just call like, you know, the state 0, and it will go right to state 0, and it will talk about state 0. Oh, and we also have to keep track of the current state. Okay, so we have action true. The action will be true. So C jump is going to be, if they cooperate, then jump to state 0. Oops, I don't want to have it on this move. They cooperate, jump to state 0. Oh wait, it's not comma, is it? It is comma. Okay, good. If we cooperate, then jump to state 0. Otherwise, if we defect, or let's just say cooperate is going to be 0. Effect. We jump to state 1. I think we should name it. I think we should name them jump, just to make them easier to understand what exactly they're doing, exactly their purposes. Random jump, it's going to be to 0. We don't really care about random jump. Random value, and just say it's 0. This is 0% probability. And then random flag, it's going to be false. So we will never jump to random. So now, action equals false. This is the if they defected. We're going to jump to state 1. This is state 1. Remember that most programming languages, and including JavaScript, are going to start counting from 0. So this is the 0th object in this array. This is the first object in the array. This is the second object array. This is the number 0. This is number 1, number 2, number 3, etc. Keep all the R's the same. This time, if they defect, and actually, yeah, we're gonna keep the actions just the same. So now we have to fill this with, I guess, this. I guess we'll fill it with this. Oh, we should probably put these on separate lines. Yeah, I'm gonna put these all on separate lines. Boom. 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 Oh, damn. Boom. Boom. Looks like we missed one. Boom. Looks like we missed a state down here. So state 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. We have the right amount of states. I'll just say this is filler. Oops. We'll just add it in. Okay, so this is a tit-for-tat brain. Now, let's make a different brain. Now we can just call brains.tit-for-tat to load up the brains. So add the brain. Now, let's make a different one. Always cooperates. Defect jump is going to be 0. It's going to be true. It's going to be really nice. We don't really need to edit anything else, but who knows? Always defect is going to be the same thing, except false. What else? We'll make this. I don't want to put a number in a variable name. We'll make this just random. This time, C jump is going to be 0. D jump is going to jump to this object. We're going to jump to itself. We're going to jump to itself. But if it's random, if we get the random number, then we'll jump to 0. Or we'll jump to 1. Then here, same thing. This is going to jump to itself. And jump to itself. This one will be false. This state, it'll jump to itself all the time. But if it gets a random value, it will jump to the other one. Okay, so, which is 0. The random value on each of these is going to be 0.5. What else? I think that's good for random. What else do I want? There are some other strategies listed in this video, so let's take a look at them. Or I'll just take a look at them alone. Oh, there's also Grudger. Let's make Grudger. Basically, Grudger starts off cooperating, but if you defect, it will never cooperate ever again. So it's nice, but if you defect, and we'll set these flags to false again. Zero, zero. It will cooperate. And if you keep cooperating, it'll keep jumping back onto itself. But if you defect, it will never cooperate again. It will go to this state and it will just keep doing itself. Keep that phrasing came out wrong. It will keep going. That phrasing came out correct. Keep going. That's the phrasing that I wanted. Okay. I can also probably something like this just to make it a little bit, I don't know, I guess better looking. So yes, that's a grudger. Maybe we'll make like tit for tat. Let me listen to what Joss was again. Okay. So let's do forgiving tit for tat and Joss. Forgiving tit for tat. Tit for tat. I should probably make this capitalized like camel case. Tit tar tat. Tit for tat. Okay. So. Well, actually, I want to instead copy tit for tat. Here's tit for tat. But instead of jumping to 1, I wrote it down right here earlier. This one jumps to 2. And it keeps jumping to 2. Oops. I didn't mean to do that. And everything else is the same. Okay. What else? I want to make Joss, which is just tit for tat, but sometimes it'll try to sometimes the random flag true. Let's say it has a 10% chance of retaliating. Of not retaliating. Of just randomly saying no. Of randomly trying to defect. Oh, wait. I think what happens with tit for tat is that it will only retaliate. It won't sometimes randomly forgive. That would be interesting. Mrs. Joss. Okay. So it'll sometimes randomly retaliate. Same basic logic as tit for tat. But our jump it'll jump to 1. And it will sometimes retaliate. It will sometimes test the waters. So that's kind of Joss. Okay, so tester is a little bit more complicated. It's a lot like Joss, but it cooperates again. So, and then I think what happens, yeah, let's try this. So it will, let's write this out on paper a little bit here. I don't want to plug in my drawing tablet again. No, never mind. Just hide that for now. So tester, let's say that randomly it'll jump to state 2. And this one, it will try defecting. Actually, it's false, because false is defecting, and true is cooperating. Just to make it probably a little bit faster, I'm guessing. That would help make it faster, the program. So, it's going to jump to this state. And if they defect, it's going to jump to state 0. Wait. So before the round, it's going to jump. And it's going to do this. Okay, let's figure out a specific order of operations here. So, we'll do exactly what order does everything happen in. So we're going to have the random jump, then we'll have the action, whether you cooperate or defect, and then you'll have the conditional jump. Okay, so it'll randomly jump to this state and it will try to defect. And then if in the next round Yeah, if they defect at the same time that they defect, then I guess it will just jump to just jump back there. But if they cooperate, then that's what it's normally doing. So it'll jump to 3. So they'll cooperate this round. If they defect, then they'll apologize. Yeah, this is going to be interesting. Yeah, who knows? I'll try defecting, and I'll go here. Yeah, if they defect at the same time as them, then I guess they'll just get back into the normal tit-for-tat thing. And then, yeah, if they cooperate, which is probably what's going to normally happen. And then if the next round they defect, then we'll jump to the apologize section. And it'll never defect again. And let's just make this. So this is 4, and this is 5. We'll just make this a tit for tat. Yeah, well, no, that's really interesting though. Because, yeah, what happens if, like, they apologize? Like, what happens if after this, they kind of start acting all, they start, like, kind of defecting? Like, what if, you know, they defect later? That's interesting. Let's just put that there so I can come back to that and think about that. Yeah, and they'll basically just jump. They'll just basically be like, hey, yeah, thank you. Or maybe, I think what will probably happen is that it'll probably just jump back into tit for tat, into the normal tit for tat thing, and then might test again. C jump? Yeah. Just jump into cooperating always. However, so this is However, if they cooperate, then we'll jump to a different condition. We'll jump to, this is 4, this is 5. We'll jump to condition 5, or state 5, and then this state just goes back and forth between defecting and not defecting. Yeah, so if they cooperate, then jump to 6. They cooperate again, jump back to 5. And move this to here. This is filler. This is the decision-making one. Then this is the test. And then this is the result of the test. Yeah, so it'll jump back and forth. Boom, 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 boom. And then, yeah, I think if it defects at any point, then it will just go back to the normal tit for tat. Yeah, this is the, I mean, in all of these cases, if it defects at any point, then it will just jump back to tit for tat, except tit for tat, except in the case that it defects as a result of it testing the water. Okay, I think that's all of them. So, let's save this really quick because I don't think I've saved this at all. That would suck if I didn't save this. I think we've generated a lot of good. I think we've filled out a lot of good brains so far. So yeah, let's make a rounds. Let's make a let's make a round function. Also, we need to add in the constant payout table. We'll make this an array of arrays. It will be 3, 3 if they both cooperate. 0, 5. Oops. Oh wait, we probably don't need that. We could probably just make it in here. So first, let's generate some individuals. So what did we say that the individuals wanted to have? We wanted them to have an ID, randomly generated probably. lifespan. So that's how long they've been alive. We'll set that at 0 for now. We want them to have a hash. We'll figure that out later. And color, we'll figure that out later. And we'll actually have a variable. Call them agents, because I'm very fancy. It's going to be an array. It's going to be an empty array for now. So, say variable counts equals, sure. Let's just generate 5 tit for tat agents. So for variable I equals 0. I is less than 5, I plus plus. It's probably an easy way to do that, but that's the way I like to do it. We're going to make a new variable called this agent. It's going to equal this. It's going to equal array. It's going to equal a this. Then we're going to say our agent dot ID. Ooh, we're gonna have to generate a random ID. Is there a way to convert things to hexadecimal easily in JavaScript? I want it to be in hexadecimal because it looks cool. JavaScript. Okay, yeah. So we'll rand equals, sure, random equals math dot random. Is math dot random correct? We'll just say this real quick. Console dot log random. This is the first time we've run this, so I don't think there's going to be any issues, but there could, I guess. We'll just log the random. True is not defined? That's weird. What? How does the true not work? That feels so weird. What the? I should leave this open like this. You got a PB! 106.34. Hell yeah, good job. JavaScript variables. I'm so confused. JavaScript, yeah, what about Booleans? Is it lowercase? Fuck, it's lowercase. Okay. Well, yeah, now the R's are all in 18. Well, good thing we have find and replace true with true, case sensitive, replace all. Same with false, replace all. Thank God for find and replace. I said replace all. There we go. Okay. All right. Our agent.id equals random dot. I'll pause this for a little bit. Random times, we'll do like what? 1 million? Let's do 100 million. I've given a TikTok from somebody named Jake the Linguist.
People from all over the world speak in different ways, right? We call these accents or dialects. So someone in Toronto, New York, and Melbourne will all speak differently. But there's actually evidence that people speak differently in outer space. And I'm talking about aliens.
Okay.
We're talking about astronauts. So there's actually been research that's shown that astronauts come back to Earth with an accent. And to understand why, we first have to understand how sounds are made in the first place. So vowel sounds are made with the very back of your tongue. If you say E and then you can feel the back of your tongue moving up and down. Here on Earth, when we pronounce vowels, we're fighting against gravity, which is pulling our tongue down. But in space, there is no gravity, so astronauts get used to pronouncing vowels with less articulatory effort when they're in space. Then when they come back to Earth, the astronauts are faced with gravity pulling their tongue down, which makes them pronounce vowels with lower tongue position. So for example, one astronaut pronounced the vowel E more like I, so instead of saying eating, they said something more close to eating. But of course, after some time on Earth, the astronauts get used to the gravitational pull on their tongue and the vowels return to normal. People from all over the world...
Interesting. That's really interesting. Times... Okay, so let's... Yeah, we'll do random times 1,000. This doesn't make sense right now. Okay. So, then we'll take this. And then we can do something like parse int this, and then the radix is 16, I guess. Oh, wait. What if I did something like times 0, 0x, no. 0x1. Jillion. Yeah, I don't know. No, not like that. Okay, so you need to convert it to a string first. Times a million. We'll do, I think we can do a lot more. So we'll do, let me just add in these commas. These commas don't make sense, but let me just add in these commas just to make it make sense to me. Okay, we'll do it times a billion. Multiply this times a billion. Floor this. So now we're getting a random big number. Then we will dot to string 16. And then I kind of want to just get like bottom 3, so I'm gonna have to figure out how to crop a string. String dot slice. And then we'll do dot slice. And then we'll just do that. Variable ID will equal random dot slice. Random dot length. Dot length. Oh, I think I need a parentheses around that. Dot len. Random dot slice, random dot length, dot length minus 3. Oh. That's a Java. That's a Java method. Well, JavaScript length. String length property. Dot length. Oh, you don't need this thing after it. Oh wait, I think you need this minus 3. Log ID. We'll do minus 5. So you can get a 5 character string. Okay, cool. So now we're generating random IDs. Variable our agent equals this. Dot ID equals ID. There we go. So now we have generated some IDs for them. Agent dot life equals 0 for now. We won't do hash and color, but our agent dot state equals I don't know. What I could actually do is I could make a different function to generate an agent. And I could say, hey, I'm going to do everything that's inside of here. Variable our agent is that. We can do everything a little bit like this. And then we'll return our agent. We can get rid of this. State equals state. We'll take in state. So now we have a function that generates an agent. And then our agent dot current state equals, start off on, 0. I forgot that we aren't doing the letters anymore. So then, in this for loop, we will instead we'll say generate agent, and the state is going to be tit for, the state is going to be, where is it? Brains.tit for tat. So put that into here. Our agent.state will be state. Return our agent. And then we'll take this, which is our new agent, and we will attach it to the push. We will push it to agents variable. Agents.put.push, generate new agents. based on the brain tit for tat. It's perfect. Now, let's, after this, in setup, console.log agents. Boom. All right, now we have a few objects. This is our object. This is the state. Here we have, they're all different IDs. Look at that. And let's look at their states. Perfect. Perfect. All right. So we can do state 0. We can call state by calling state 0 now. Okay. Cool. Agents.push tit for tat. And we'll say this is, we'll just say this area is generate the agents. So we'll have tit for tat. And then we'll have, this one will be, sometimes they'll be random. Some agents will be JOS, sure. I'll have 5 these, 5 these, 5 these. Console.log agents. Now we have these. Oh, you know what I also want to do? I want to add, what if we add a name to each of these? State, and then brain name. So then we had, so we said state, and then let's just call it type. Our agent.type equals type. Then we'll say brains.tit for tat. Tit for tat. So this way it's just easier. We can see it in here. It's .jos. JOS. I'll have 10 tit for tat agents. Fuck it. Tit for tat. This one's gonna be tit for tat, and this one will be random. And then this one will be random as well. This one will be JOS. Perfect. This one will be JOS. Awesome. Incredible. Okay. So now we have these objects. Now we have these agents. Let's make them fight. And I also want to show the rounds on this thing right here. So let's make a function. Let's call it round. So make a match then. Function called match. That's weird. Why do we already have rounds and matches? P5JS? P5JS? Give me the reference. Background. Oh, we have. There's already a math calculation that is round. Oh, match. Oh, there is. There's a. Wow, that's just unfortunate. We just so happen to be conflicting with P5JS. Let's call it battle. So, battle, sure. And then for variable I equals 0, for I is less than 20, I plus plus. Is it semicolons? Am I have how did I forget that it was semicolons, not commas? Okay. So in this battle, this is going to be a really big for loop. Battle between Agent 1, Agent 2. Make it a little bit easier on ourselves. Agent A, Agent B, because we're going to be dealing a lot with numbers here. Agent A how are we going to do this? So let's start off with random jump. The random jump I'm going to make the action. We're going to determine the outcome. And after the battles, okay, well, no, we'll figure that out later. We'll determine the outcome. Do points. Then we'll do a conditional jump. And then I think that's it, right? So, We'll also keep a variable, global variable, battles. Store this information. So we'll start off with the random jump. So state's current state. You know, maybe instead of naming it current states, I'll just name it like cur. Just that it makes it a little bit shorter. And then I'll add a note. So, if, let's look up here. Our flag, if our flag, so if agent A, well actually we'll do, yeah, if agent A dot state current dot our flag random equals, we can reuse this variable, math dot random and if random is less than rval. Then agent A dot current state equals our jump. So now sometimes it'll randomly jump. Make this one. Do it once. Okay. Yeah. No, I don't want to have that one. Yeah, sure. And actually, you know what? I want to try this out. I want to see if this works. I'm pretty sure it does, but let's console.log agent A.current. So then in the setup, we'll just say, I don't know, battle agents 0 and agents 1. Cur is not defined. Oh, state. Agent A dot cur 0. Oh, right, because it's all, let's do agent 15 and 16 then. I think that's technically the second and the third. But rval is not defined in. So then, agent A dot rval. There we go. Let's do that again. See if it changes again. Interesting. Equals yeah, I've kind of fucked this up a little bit. Agent A dot state agent A dot current dot rjump. Oh wait, let's console.log this. Okay, so it is going every single time. That's good to know. Random equals math.random if math.random is less than agent A. Oh, agent A dot rval. Agent A dot state. Let's just say this. A state equals this. Variable. If a state dot r flag is less than a state dot r val, a dot current equals a state dot r jump. Okay, so let's do this. You can see it jumped. It did the test jump. We haven't included any of this conditional stuff, but did the test jump 3 in. Here it did it 5 in. Did it 8 in. 6 in. 9. It didn't do it at all there. Oh, it did it at the very end there. 5 in. Oh, it did it first thing right there. Did it 8 in. 10 in. This is nice to see. Nice to watch. Okay. So that's definitely working. Same thing for B state. B state equals agent B state if B state B state agent B. Perfect. Okay. So now let's see what this other guy's doing. Let's do both of them. Console.log agent B.current state and let's console.log agent A.current. Oh, yeah, that's gonna be. Oh, let's console log them together. And space and agent B.current. Ooh, interesting. That time neither of them did anything. This time, that one didn't do anything either. Wow, they're a little shy. They're both a little shy. Oh. Wait, no, A is a bit shy. Probably because I got rid of the changing of A. Oops. Agent A. There we go. Oh, they both changed at the same time there. That's interesting. Of course, we're doing this on two Joss players, but we haven't coded in the conditional logic. And normally, the conditional logic would mean that against tit for tat, it just goes kind of back and forth. Against tit for tat, it will try once and then it will go back to being normal. Because I think Joss, it has true here. And then it basically... Oh wait, well, it jumps to false, but then it basically immediately jumps back to true. Okay. I'll probably get going at about 5. I'll probably pause the stream. I might end it and then start it back up again. But if not, I might just put this screen on or something. While I'm gone, I'll go get something to eat and then I'll come back. Because I actually woke up pretty recently and I had this idea last night and I just had to wake up early in order to I just had to go to bed and wake up so that I could I woke up and I immediately started working on this because I had this great idea. At the same time again. We never switched over. Yeah, so we have the random jumping. Now we need to do the action. Variable, we'll save the action. Action A, variable, action B. So A, the A action is going to be we'll actually reset all of these values after this. Say A state equals state. Variable action A is action A is a state dot action. That's what I called it, right? A state dot action. Action B equals B state dot action. And actually, you know what? We'll have variable one match, because I know that variable name is going to conflict with the thing in p5.js. One match equals, I would just do match, but it's this, and we're going to, I'm going to make this an object. And then one match equals, or one match dot a state equals a state. One match dot b state equals b state. Pretty simple here. Then we'll do one match dot action A equals action A. Surprise, surprise. One match dot action B equals action B. I should probably keep this in the same order. So I should probably keep this like A action, B action. Okay. Perfect. Now we've saved the actions that these two agents are going to take, and we saved the one match. Also at the end here, we'll take one match, and we will, or battles dot push one match. So now we're going to save everything that happened in here into battles. We should save. Also, we should have we should have points. 0. Everyone loves points. So we determine what action they're taking. Then we'll do like a truth table. If A action, do this. Else if we do this. So basically, if A cooperates, then we do what's in here. If A does not cooperate, then we do what's in here. And then we'll say another if B action. So if B cooperates, okay, I think we can make this seem a little bit simpler if we just do A action and B action. Else if A action and not B action. Else if A action if not A action and B action. Else if not A action and not B action. And then it shouldn't make it past any of this, but else we just say console.log. Fuck. A action and B action. So if they both cooperate, then agent A dot points plus equals 3. Agent B dot points plus equals 3. Perfect. If A cooperates and B betrays, A gets 0, B gets 5. If A betrays, A get 5, B gets 0. They both betray, then they both get 1. How do you like that, Obama? And then I want to see. Let's do console.log agent A.points plus space plus agent B.points, not as a string. And then we'll also we'll add in a space in this and a space in this, and we'll add in a state. Oh, it's not. Agent A dot current state number. Oops. Damn. Fucking racking up points. Oh my god. Agent B by switching over. current. Okay, so now we can see what state everything's in. You can see, let's get one where they don't immediately do anything. You can see, all right, so now they're both in state 0. And they're gaining points, 3 points every round. This one switches to state 1. It immediately starts racking up 5 points per. And then eventually this one switches to 1, and they start racking up 1 point each. Obviously, we haven't implemented all of the logic yet. We still haven't implemented the conditional jump. So these aren't like actually playing with each other right now. What if instead we had Agent 0 and Agent 1? They're tit for tat, and they will, yeah, it's going to be the same every single time. They will never fight each other. They'll never do anything to switch states randomly. So yeah, let's put this one up against Agent 16 now. This one's always going to beat this one because, or tie, because it will always switch over to the defecting, and the other one won't do anything. So now let's implement the conditional logic, and this will really make it shine. Hold on, let me turn on my light. This will really make it shine. This is really where they're actually going to be fighting against each other, I guess. So, at least just the individuals. The agents. So, we'll say if A action and we don't even need to do any additional like equals things. If A action, so if they cooperated, then it's going to state equals C jump. And then agent B dot current equals B state dot cooperate jump. Else current equals B state dot defect jump. That means that it defected, so it's going to jump. However, tit for tat isn't going to defect. Same down here. Except everything is reversed. If B action agent A dot current agent A and A. Oh, that's nice that it's all A, B, C, D. It was not intentional. Oh, yes. Look at that. We're getting the defection echo now. Look at that. Wait, what? I'm so confused. Wait, is that one supposed to be... Isn't agent A That's Agent A. Why is Agent A suddenly defecting? That doesn't make sense. Is it specifically on that one? Oh, it might be just because, yeah, it's just because of where this thing is. So if I put this right after everything, right after this stuff, there we go. Then we see what state it was in when it made the decision. So it was in this state when it made this decision, and then it was like, hey, you cheated, 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 blah 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 blah. And then it's Joss. It didn't do it again. It didn't switch back. Cooperate. Ooh, look, they cooperate all the time there. Here's a good example of it cooperating all the time. Boop. It's like, okay, I'm gonna test. Joss is gonna test it. It's gonna be like, hey, you cheated. 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 And then it's gonna get down to here, and it's going to try to test it again. It's just gonna randomly do it again, and then it's just gonna stick. All right. I think that's all. I think we have. Yeah. What is in one match? Okay. Okay. Now, what I think I'm going to do is I'm going to draw these out. So I'm going to draw in little squares. Let me actually show you my plan. I'm going to draw out this is the gradient tool. Try to find square tool. Perfect. Rectangle. I want to draw kind of full solid color. Draw a filled shape. I want to kind of have like tiny little squares like this that represent defecting or rejecting. So then this person on the bottom here kind of do that, and then like that, and then like that. And then if somebody cheats, it turns red. And then if it's like tit for tat, then the next person draws in a red circle. And the next person gets a green circle. It's like, oh yeah, I cooperated. And then you defected or whatever. Okay. So in draw, let's actually per battle. We'll have this constant matches per battle. And we'll say 20 for now. And then we'll also have some square width, and we'll say square width will be 5 for now. Four. I equals 0. Where pause this. I'm a little nervous of making for loops while the thing is running. I is less than matches per battle. So we'll be doing this 20 times. We'll be doing what's inside these curly brackets 20 times. I plus plus. Constant x offset from the top. We'll make that 20. Y offset from the top. We'll make that 20. So we have all of these battles. Battle equals battle I. So now this current battle should be an object. I hope he heard me say that say nice. So I'll message him directly. What happened to Obama? All right. So then we will say draw a rectangle. Oh, and we'll also set fill. That'll be a conditional. We'll say, let's just get the shapes down first. Rectangle at location. This will be x offset. Plus square width times I. Y offset. Let's just create the first row. Y offset. We'll make it square width. Square width. Boom. Perfect. We have those. Let's make it a little bit bigger. Let's make it 10. That's about the size I want. And then we will say, what is it? What is it? It's like line. It's like border. What is it? What is it called? What is it called? Shape. Stroke. No stroke. Do no stroke. With no stroke, and then we will do. We'll do fill a little bit later. Yeah, let's figure out fill right now. So we'll say if battle current battle dot a action. If they cooperate, then fill green. Else, fill red. Oh, I have to put it in like quotes. There we go. Look at that. Now it's copying what this one does. Oh, look, it probably defected twice in a row. Must have randomly defected twice in a row. How does that happen, though? I don't think that could happen. Joss. So, it must have defected. Must have conditionally jumped to here. So, conditionally jumped right before this to 1, and it defected. Then, should have jumped to 0. Oh, it jumped to 0, and then it again conditionally jumped back to 1. Okay, that makes sense. And there we have the defection echo. Except we don't have 2 rows yet, so we'll do that. Then we'll do this. Except we'll fill out with, say, B action. And we will say X offset plus square width times I. And then Y offset plus square width. So that's 1 down. Boom. Now we got that. And we also don't really have to. I don't really need this console that much. Yep, now you can see the defection echo there. Boom. Look at that. Let's put a Joss up against a Joss. 15. 16. Oh yeah. Pretty much the same thing. They both defect at the same time. They both got through that game cooperating. Look at that. Looks so cool. Alright. Let's pit... Ooh, I want to see what happens when we pit a tit-for-tat player up against a random player. And that should be 10? Oh, yeah. Honestly, I kind of want to get rid of the top row just so that I can convince myself that this is random. Yeah, that's pretty random. Can't see any reason that's not random. You know what I want to see now? I want to see... tit for tat. Tit for tat. Up against... forgiving tit for tat. And just do T4T. Up against, we should also add some grudgers into here. Grudger, and then this one is going to be, what is it? This one's going to be Tester. I want to see if Tester works. Tester. Forgiving tit for tat. Yeah, okay, let's put Tester up against 10, 15, 20, 25, 30. So I'll do 29. Should be a Tester. Oh yeah, look at that. Look at that. Tester up against tit for tat. It's like, oh, sorry. I'll apologize. Let's go. But, oh, I want to see what happens when it gets put up against a forgiving tit for tat. So let's do this. Oh, okay. So there's obviously an error or something. Let's see what's wrong. Let's put forgiving tit for tat up against... Yeah, let's put them up against a random. So that would be 10. Oh yeah. Yep. Forgiving tit for tat is working. Yeah, so it's clearly Tester that's not working. Okay, let's read through Tester again. So, it'll start out on true. Maybe we could draw this out a little better. Maybe we could draw this a little bit nicer. So we're going to start off on state 0, start on state 1, but sometimes state 0, go to state 1, but sometimes randomly pop over to state 2. And state 2 is going to be state 2 is going to be waiting. Oh, wait. So sometimes for it'll jump to state 2 and it will say false. Say haha. Let's actually do forgiving tit for tat against tester. The thing is, it should be really taking advantage of forgiving tit for tat. Okay. So, this is the state that it's in. Oh wait, this is the test state. And then it'll jump to state 3, which is like a wait state, a waiting state. It's where it waits for the other one to do something. 4 is a nice state. Oh! It's probably going back and forth between... Yes! Yeah. I don't know why I didn't read this. It's going back and forth between 5 and 6. Problem is that 5 and 6 are just both true. So it's not... It's recognized it, it just hasn't taken advantage of it yet. There we go. Boom. Time to take advantage. So that's what happens when it goes up against forgiving tit for tat. And then, of course, when it goes up against regular tit for tat. Zero is regular tit for tat, right? Yeah, it's apologizing. Boop. And then it never tries to test again. Whereas Joss will try to test again. Joss 15. It will go boop, boop. Boop, boop. Boop, boop. All right. So, let's put up against Grudger. Let's put, what was it? They're both testing strategies. I think this one's Joss as well. Okay. So 29. It's gonna be tester, and then I want to see what it's like up against grudger. It's obviously just gonna hate it. Okay. Yeah. Oh, okay. Sorry. Oh. Oh wait. You actually just hate me though. Okay. Never mind then. Here it is. Here grudger is responding, getting a grudge, and then here it is being like, oh shit, I'm sorry. Okay. And then it gets and then it's still angry at it, so it's just like, oh fuck you. That's just gonna happen every single time. Okay. So now we have this. Now what I want to do is right above, I want to draw in the state. I want to draw in like the state, which is going to be like a color. You know? So I'll have up here constant state colors. And we haven't made the genetic algorithm yet, but I'm thinking I'll probably do that after I get back from eating, which I'll probably do pretty soon. Oh my god. I'm just going to let you know that the Obama server is having one because the admins have renamed it to DaBaby. This is very entertaining. I've made it a DaBaby server now. And I think it's like crashing Discord or something. It's just destroying the servers. Oh, God. Oh my God. Yeah, it's just... What the fuck is going on? Holy shit. It's like literally crashing the server. Just how many people are typing. State colors. Oh, I don't want it to be like that. Because the states are all numbers. I can just put them in an array. And then it'll just automatically sort things based on their numbers. Could you imagine trying to moderate this chat? Okay. So what colors are there? 5.color. Colors. Oh, is there like HTML color names? Are these all supported? So like if I make green like aquamarine instead. Antique white. If I make that like antique white or something. Oh, okay, cool. They're all supported. What's the most interesting one? I want to see just to make it look interesting. I want to see tit for tat up against random. 0 against 10. Okay. So it looks like all of these colors right here are supported. So let's see what colors we want to make them. This place is just going insane. Oh, 6-hour slow mode. Forgot. Even with a 6-hour slow mode. Oh my god. This is probably the biggest server I'm in. 30. It looks like there's about 35,000 people here, and yeah, we all just got pinged, so makes a lot of sense. Is going. Also, I do not condone any of this shit that's being said on here. I run the risk of showing something inappropriate. Okay, so what colors do I want to make everything? We have red and green going on there. Let's say that the first one is let's say the first state is, I don't know. Say it's, let's do some very big colors here. Let's say it's yellow. Then we'll say just regular blue. Then after that, orange, I'm guessing, is on here. Orange. Orchid. We'll go orchid. Go saddle brown. Let's go silver first. Silver, saddle brown. 1, 2, 3, 4, 5, 6. Spring green, I guess. Salmon. Okay, so we have red, orange, yellow, green, blue. We could do like a darker. We could do like a different color, purple. We could do like a pink. Yeah, let's do like indigo. No, purple. Let's do like a hot pink. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I think we can replace one of these colors. I don't know. Let's see them all together. See what they all look like together. So, down here in the draw, I'm going to say square width times 1. I'm going to have these all be... Oh. This one will be square width times 1. This one will be square width times 2. And then since we're doing something above it, we just have square root times 0. Square width times 0. Perfect. Fill, fill. Let's do with what was it? State colors. For I mod 10 for right now, so that we get all the colors in a row. Okay, so that indigo looks way too close to the blue. And the orange looks pretty close to the yellow. Let's make that black. Oh, and orchid looks too close to hot pink. Black. Let's make this. Let's not make that silver. I don't like how light that is. What about, like, is there like a dark gray? How about dim gray? And that's, of course, 696969. Nice. Dim gray. How about instead of orchid, it's dark violet? Oh, those two look too close. Salmon and hot pink. Well, how do they... Okay, all three of those colors look too close. So dark violet, and then we'll change... I don't know, salmon to... cyan. Fuck it. Oh, that looks really close to sea green. That's not brown. The fuck? Let's temporarily make the size a little bit bigger, so I can see it a little bit better. Let's make the canvas, just in general, a bit bigger. It's generally a good idea. Yeah, the salmon and the hot pink are very close. What should the salmon be? We don't really have any good red colors up here. So let's do Indian red. That looks nice. Oh, that looks really close to that. Let's do maroon. Oh, that's gonna look very good. So we're going to fill this. Instead, we're going to fill the state colors with a state. Oh, current battle dot a state. A state. A action. A state equals A state. Current battle dot A state. Why is this erroring out? Sol.log. Current battle dot. Oh, current. Yeah. Oh wait, no. That should work. Oh. Battles dot. Oh. Not dot A state. Dot. Oh, shit. No, come on. Dot. Equals agent A dot current. Agent B dot current. Okay, yeah, you can stop console.logging. Fill with state colors for current battle dot a state. That's actually. This battle equals this thing, and we're instead going to let's not complicate it for right now. Oh hey, look at that. Works out really well. Looks a little bit ugly, but we won't mind that. And then boom. Times these three. Battle.b state. I think what I want to do is I want to have the height for these things to be a little bit smaller. So let's do that. So let's do square root divided by 2. Hopefully that will, it's the wrong dimension. Divided by 2 times 0.5. Zoom that down a little bit. And then we don't need to do anything here. Just need to do square root times 0.5. Boop. Now you can see what state everything was in when it made the decision. Okay, cool. Let's make everything a little bit smaller, I'm gonna say. Okay, that looks interesting, but so you can compare it to the minds of them. It doesn't look that interesting because it's still just tit for tat versus random. So I'm actually really interested in tester, how that would look. So this is going to be 10, 15, 20, 30, 35, 34, I think. We tester. I guess maybe not. Maybe it's 29 is tester. Oh yeah, you can see they test and then they apologize and then move on. This is kind of their brain. And they won't test ever again. Okay. Now I want to see tester versus tit for 2 tats. Oh, it tests, then you can see it's waiting. Oh, that's the waiting phase. Tests. It's waiting. This one's like, okay, this is the forgiving tit for tat, so it only changes when it's on. I think it's when it's on orange. Yeah, when it's on orange, it only retaliates when it's on orange, so it learns it can take advantage. That's interesting. I like that. I like this a lot. Okay. What else can we do? What else can we do? Just temporarily, for now. Let's fucking go. Let's add in. Let's add in the ID. Okay. Let's make this a little bit more accurate. So right now we're just saying battles equals this. But we want a battle to actually be, wait, no, I think we're good. Let's have battles. Battles is an object. And we'll say Nah, let's not do that for right now. Okay, let's set it up for when we do actually have multiple battles going at once. So, these are the battles, and each battle is going to be variable. This battle is this. So, this battle dot agent A equals agent A. This battle dot agent B equals agent B. Agent B. And then this battle dot A points equals, we'll put this at the end. This battle dot agent A points A dot points agent B dot points B points. And then we'll say this battle dot matches equals, this is going to be an array. One match equals this. Dot matches dot push one match. That's what it's called, right? Yes. This battle points, and then we will battles dot push this battle. So now the issue is that everything's kind of referenced differently. So we'll say it's not battles.I. It is matches I, but it's battles one dot matches I think, right? Oops. It's an issue. Undefined. Battles one or it's battle 0. I don't know how I didn't realize that. Okay. Okay. What were we doing? Oh yeah, we were let's do equals current battle dot matches I. A battle is like a game of 20. I should call it a game, but I couldn't think of a good word at the time. It's like a game of 20, and a match is a specific round, you know? Matches. And a lot of these are going to be current match instead of current battle. Current match. Current match. Current match. And this is also current match. Perfect. And then we want to add in the IDs of them as text beside everything. Text, and we'll say that we'll just say fill with black. Text. How do we do text here? Text, we'll type in whatever text we want. So this is current battle dot agent A dot ID. Let's say 0, 0 for now, just to make sure that works. It does not work. Say it's 16 for now. Fuck it, I don't care. This battle. Agent A. Yeah. How do I... What? I'm so confused. Oh god, I made a mistake by putting it in here. Dot ID. Oh, is it that there's stroke 2 or something? Oh, it's like off screen or something. Let's do 100, 100. There we go. Okay. So, we're gonna place this kind of on the left here. So we're going to place it in offset plus square width times plus x offset. Agent B will have this one square width times 2. Yeah, that's just gonna move it down 1 square. Let's move it down. It's times 3, like 3.5, I think. That make it centered on. I don't know. Let's just make it 4. Okay. Let's have it like this. 1.5. Times 0.5. And then plus x offset times 0.5 as well. Offset plus square width times 0 times 1. Okay, so the bottom center is like there. So that's where the bottom center is. And the bottom center is here. Okay, let's make this square width just to make it easier. So that means that I would have to move it down by half a square width. Yeah, 1.5. Okay. What if I did like a stroke of like 1? 0.5. So basically, see, stroke 1. And then we will make, I don't know, the text no stroke. Design. Interesting. Holy shit. Oh, there's some. Yeah, damn. That's some bad fucking. Sorry, I'm a little distracted by Dream getting rejected for cheating. That's interesting. A Minecraft speedrunner. They've gone through a full fucking analysis. I really want to read this whole thing. Okay. For ender pearls. What is this? Okay. Highest probability. .04 times 10 to the negative 10th represents the highest possible probability of Dream ever while on stream getting pearl barter rates as exceptionally good as the ones he got, as the ones in the data. Across 1,000 runners. Eight times 10 to the negative 7th is the probability that any active runner in the Minecraft speedrunning community would ever experience events as rare as Dream at some point within his 11 streams. Experiencing luck extreme enough that a malicious investigator would be able to portray it as being as rare as Dream's bartered luck. The events that were reserved on Dream Stream could not be modeled by any sensible conventional probability distribution. After accounting for any contributors of bias, the likelihood of this occurring is still unfathomably small. There is no circumstances in a natural setting in which bartering and blaze drops can be dependent or biased to any notable degree, much less a degree strong enough to produce this result. There is no way to accidentally manipulate these values in real time during an RSG speedrun, nor any conceivable way to do it intentionally using only conventional methods. That is insane. Okay, anyways. Kind of like this. I wonder if I should instead draw like a line. Line, and then I'll say like stroke 1. I'll say, yeah, stroke of 1. Draw a line starting from, it's probably like X, Y, X, Y. Line. Yeah, it's X, Y, X, Y. Starting from, what is it? It's, x offset plus, I don't know, square width times 2? Y offset, comma, offset plus square root times 2, and then y offset plus square width times matches per battle. Looks like we got everything kind of in the wrong order. That's weird. Maybe I got things in the wrong order, so it's like y offset, x offset times 2 is 2, x offset times 2. And then if I get rid of, okay, no, it just doesn't exist. You know, if I get rid of stroke, oops, everywhere except for that one line. Let's do 2. I don't like the line. Let's yeah. I might come back to it later, but I don't like the line for right now. Okay. All right. I think we're good for now. I'll probably come back to this. Oh, that's weird. Failed to save sketch. It's open in another window? What? I don't have it open in another window, though. That's weird. It's not on here. Save. Please refresh to see the latest version. Just duplicate. We'll just leave, and then we'll say no stroke. No stroke Damus. No stroke. See? All right, perfect. I think we got some good shit done. I'll go for now. I might make a part 2 of this. Maybe tonight. Who knows? Where I actually do the genetic algorithm thing. All right.